Hello everyone, welcome to Math 115, College Algebra. So in this section, 4.2, we want to talk a little bit about modeling with linear functions. So basically solving some applications that involve linear functions. So to start, let's look at this first example. So we're given a table and we're told that this table represents a linear function, right, or linear equation, and we want to complete the table. We want to fill in the missing values in the table. So first of all, if this is a linear function or linear equation, notice here that if I look at the input values, they're all increasing by 1, right? Plus 1, 3 to 4 is plus 1, 4 to 5 is plus 1, and 5 to 6 is plus 1. And the output values, in order for it to be a linear function, it must have a constant slope. So the output values must also increase by the same amount, right? And in this case, I'm going from -4 to -2. So I'm going up +2, right? It's increasing by +2. So that means the next jump must also increase by +2. So -2 plus, if it's increasing by +2, -2 plus 2 gives me what? Gives me 0. Right? Then 0 plus 2 will give me 2. Then 2 plus 2 gives me 4. And then 4 plus 2 gives me 6. So these are all increasing by +2, right? Another way of looking at this is I can calculate the slope just by using the first 2 points. So if I use this as a point and this as a point, right, I have 1, -4, and then 2, -2. Think of this as x1, y1, x2, y2. So the slope, by definition, is going to be y2 minus y1 over x2 minus x1, right? So this is -2 minus a -4 over +2 minus 1. Well, -2 minus -4 is the same as -2 plus 4, which is +2 over 2 minus 1 is 1, right? So if you think about it, this is the rise, this is the run, right? This is the rise, this is the run. So the slope here is just +2, right? So those output values have to just keep increasing by 2. The inputs are increasing by 1, the outputs are increasing by 2, and that will give us a slope of 2, right? So that's why these values have to be 0, 2, 4, and 6 when we complete that table. Okay, here's another example. Let's say now we're given the linear function in the table, all the values are in there, and we want to find several things about that linear function. We want to find the slope, we want to find the y-intercept, and we want to find an equation for the linear function. Okay, so to find the slope, we can use any 2 points, right? It doesn't matter. Let me just pick the first 2. So I'll just use these 2 points. So the first is -6, 24. So this is like x1, y1, and then the second point is -4, 18. So this is like x2, y2. So the slope is going to be y2 minus y1 over x2 minus x1. So in this case, it'll be 18 minus y1, which is 24, over x2 -4 minus x1, which is -6. Again, be careful with the signs here, right, when you do the basic arithmetic. So 18 minus 24 is the same as 18 plus a -24, which is -6. And then -4 minus -6 is the same as -4 plus 6, which is +2. So in this case, it looks like the slope is -3. Okay, what about the y-intercept? Well, looking at the table, right, remember that the y-intercept has the form 0 comma b, right? 0 comma something. Looking at the table, we have that value right here, right? This is the y-intercept. So the y-intercept is going to be 0 comma 6 in this case. All right, and now that we know the slope and we know the y-intercept, we can come up with an equation, right? Remember the equation, so I'll call it, since they're using h as the name of the function, h of x equals mx plus b. But I know now that m is -3, and I know that b is 6. So that would be the function, right? That's the linear function. So this is an h here. So h of x equals -3x plus 6. Okay, the next example tells us that a town's population has been growing linearly. Okay, so we know that a linear model will work here. In 2003, the population was 65,000. And we're also told that the population has been growing by 700 people per year. Okay, and we want to write an equation for the population, P, which we're going to call P, t years after 2003. So we want to write a function, P as a function of t, right? And it's a linear function. So first of all, what does it mean to be t years after 2003? Let me explain that first. So I'll do that by drawing a little table here. So if the year is 2003, then what is t? Well, if t is the number of years after 2003, if the year is actually 2003, then t must be 0, right? Another way of figuring it out is I could just say this is going to be 2003 minus 2003, which is 0. If the year is 2004, then how many years is that after 2003? Well, it's 2004 minus 2003. That's equal to 1. So t is 1, right? 2005, you can see the pattern here. T is going to be 2. Okay, and so on. All right, so a couple of things. From this, so first of all, the population has been growing by 700 people per year, right? That's our rate, 700 people per year. So that rate of change is the slope in this case, right? So this 700 is our slope. Okay, it's the rate of change of the population. 700 people per year. And then we're also told in 2003, right, when t is equal to 0, 2003, that's our initial or starting value. That's basically our y-intercept. Remember, the y-intercept is like the initial or starting value. When t is 0, that's what the population is. Okay, so you could also say it's like, in this case, instead of a y-intercept, since we're using p, you could say the p-intercept is 0, 65,000, right? So now I can write the formula, right? In general, P of t is equal to m, instead of x, we're using t now, plus b. Well, we know b is the 65,000. And we know m is the average rate of change or rate of change. That's the 700 people per year. So the equation or this function is going to be P of t is equal to 700 times t plus 65,000. So that is our function that gives the population as a function of time, right? And it's a linear function. Okay, how do we answer the second part of the question, which is on the next page? Well, it's asking for, and I'll get there in a second, but what is the population in the year 2009? So first of all, let me go back to this table here. In 2009, what is t, first of all? Well, it must be 2009 minus 2003, right, which is equal to 6. So t is 6. So basically we want to know what is the population when t equals 6. So to answer that, I can just plug into my function now, right? I have the function p as a function of time. So since I know that p for any time is equal to 700 t plus 65,000, I want to find p of 6, right? Because that will be the year 2009 when t equals 6. So if I plug in, wherever I have a t, I'm going to plug in a 6. So this is what, 4,200 plus 65,000. And if you work that out, it turns out it's 69,200 people. Right? They're really units, right? It's the population in number of people. So 69,200 people. Okay, the next example is similar. So now instead of people, we're talking about the moose population. So let's see if we can answer this question. So it says in 1993, the moose population in the park was measured to be 4,570. By 1999, the population was measured again to be 4,750, right? So it increased. The moose population increased over those years, over those 6 years. If the population changes linearly, so again, we're assuming we can use a linear model, we want to find the moose population P in terms of T, but now T represents the year since 1990, okay? So again, let me make a little table again. I think it's helpful just to have this table. So if the year is 1990, then that means T is going to be 1990 minus 1990, which is 0, right? The year since 1990. Well, if the year is 1990, it's 0 years since 1990. And then for 1991, T is 1. For 1992, T is 2. For 1993, T is 3, and so on. And there's a few other we need to know. We're also told in the year 1999 what the population is, right? So what is T for 1999? Well, it'd be 1999 minus 1990, which is going to be 9. Okay, and then later, since we want to answer this question, let me just do this now. What is the population in 2003? Well, what is T for 2003? Again, I can just say it's 2003 minus 1990. And that's equal to what? 13, I guess, right? So it'd be 13 in that case. All right, so in order to find this equation, this function, this linear function, I need to find the slope. I need to find the y-intercept, right? Or I could also use the point slope form. So let's start by finding the slope. I am giving two pieces of information, right? I know that in 1993, when t is 3, so I'll call this like T1. The moose population is 4,570. So this is like P1. I also know in 1999, when T is 9, so I'll call this like T2, the moose population is 4,750. So this is like P2. So the slope must be the change in population, right? The change in the output, P2 minus P1, over the change in the time, change in the input, T2 minus T1. So this will be 4,750 minus 4,570, all divided by 9 minus 3. Okay, this is equal to 180 over 6. So 180 over 6. And of course that simplifies to 30. And it really has units, right? Remember, the population is the number of moose. So it's like moose per, and the time was measured in years. Okay, so that's our slope. It's the population's increasing by 30 moose per year. Okay, so how do we find the equation? Well, I guess maybe the easiest to use here is just use the point slope form of the equation. Okay, so remember in general, the point slope form is y minus y1 equals m times x minus x1. Except in this case, we're using p instead of y, and we're using t instead of x. So I could write this, and make a little more room on the side here. I could write this as p minus p1 equals m times t minus t1. Okay, now what am I going to use for my my t1, p1? I can use either of these, right? But since I label this one t1, p1, let's just use this one, right? But I could also use this point. I could use any point that lies on the line. So I'm going to say p minus, well, p1 is 4570. The slope we know is 30. And I have t minus t1, which is 3. Okay, I'll distribute in the 30, because we probably want to write this in slope-intercept form. So I have p minus 4570 is equal to 30t minus 90. And then finally, I'll add 4570 to both sides. And if I do that, I'm going to get p is equal to 30t. And then negative 90 plus 4570 is 4480, right? Positive 4480. And that's my equation, right? In fact, that's my function p as a function of t. It's going to be 30t plus 4480. Okay, so actually that will allow us, so that's the linear function in general. That's going to allow us to solve this next question, part B here. What does the model predict the moose population to be in 2003? Well, remember, we already said in 2003, t is going to be 13. So I want to know the population when t is 13. So I go to my linear equation, and where I have a t, I'm going to plug in 13. So 30 times 13 is what? 390, I think? Yeah, 390 plus 4480. And if I add those together, I'm going to get 4870 moose. Okay, so the moose population, assuming that this is correct and you can model it to be a linear function, then in 2003, you should have 4,870 moose. All right. Few more examples. We'll just do 2 more examples for this section. Okay, let's look at this one here. So it says Jamal is choosing between 2 truck rental companies. The first, Keep On Trucking Incorporated, charges an upfront fee of $20, right? That's kind of like if no miles are driven, you still have to pay out $20, right? That's like the initial cost, or it's kind of like our Y-intercept. And then 59 cents per mile. Okay, so $20 up front and then 59 cents per mile. The second company called Move It Your Way charges an upfront fee of $16 and then 63 cents a mile. So it's cheaper upfront cost when you haven't driven anything yet, but there's a larger cost per mile. And the question is, when will Keep On Trucking Incorporated be the better choice for Jamal? All right. Right, because at some point, right, for a certain number of miles, it's actually going to be cheaper to rent from Keep On Trucking than it is from Move It Your Way. right? Even though it costs more up front for keep on trucking, the cost per mile is less, so eventually it'll be cheaper, right? And we want to figure out when that's the case. All right, so to think about this, again, these are both going to be just linear functions. So let me start with keep on trucking. So let's say x is the distance that we want to travel in miles. And I'll let C be the cost that you're going to have to pay the moving company or truck rental company. Okay, so basically for keep on trucking, we know that the slope, right, is 59 cents. So I'll write it as $0.59 per 1 mile. All right, that's the slope. And we also know that the y-intercept B, which is the initial cost, right, when x is 0, when you haven't driven anything yet, is $20. So that means the linear function must be c of x is equal to 0.59, right, m times x plus b. Okay, so that's our function for keep on trucking. All right, now what about move it your way? So move it your way. In this case, the slope is 0.63, right? $0.63 per mile. You remember that means like 1 mile, right? And then the B, the initial cost or the y-intercept, when you haven't traveled at all yet, is going to be $16. These are really dollars. This 20 here is really dollars. Okay, so that means for the linear equation, it's going to be C of x, the cost for x miles, is equal to 0.63 times x plus 16. Okay, so I want to know for what number of miles, right? This is like when will keep on trucking be the better choice? For what number of miles is the cost less for keep on trucking? That's basically what we want to know. So, well, first, to answer this question, let's just set the cost equal, right? Since these two equations both represent the cost, we're going to set the cost equal and solve for x. That's how we're going to answer this. Set the cost equal, right, for the two companies, and solve for x. So that'll tell us how many miles we have to travel for the cost to be exactly equal. Right, so if I do that, I'm going to have 0.59 x plus 20 equals 0.63 x plus 16, right? I'm setting those two costs. I'm setting these two to be equal to one another. Okay, now how do I solve for x? Well, I could actually clear out the decimals by multiplying everything by 100, but I think in this case it's easy enough. Just let me bring the x's to one side. So I'm just going to subtract 0.63x from both sides. And then I'll get rid of the 20 by subtracting 20 from both sides. So I'm going to have, I guess this will be negative 0.04x, right? These cancel. And on this side, these cancel, and I have 16 minus 20, which is negative 4. And then finally, if I divide by negative 0.04, divide by negative 0.04, I'm going to have x is equal to 100. So when Jamal travels 100 miles, both companies will charge exactly the same. But if Jamal travels greater than 100 miles, then Keep On Trucking is going to be cheaper, right? Because it has the smaller rate, right? The cost per mile is less here, right? It's only 0.59 as opposed to 0.63. So once we get above 100, then it's going to be cheaper to use the Keep On Trucking company. Another way of seeing this is to do a little graph. I think this is instructive to see this in a graph. So let me draw this out. So let's say my x-axis will be the miles. And then my y-axis will be the cost, right? C, which is really in units of dollars. And for Keep On Trucking, remember the y-intercept is the initial or starting amount, which is 20. And then the slope is 0.59. So it's going to look something like, let's say something like this. And then for the second company, Move It Your Way, it starts at 16. So this is 16, right? That's the initial cost. But the slope is slightly steeper, right? Because it's $0.63 per mile. So it'll look something like this, let's say. So the question is, where do these cross? Well, they're going to cross, and we just figured this out. Remember, we set the cost equal at that point. So where do they cross? They cross when x here is equal to 100 miles, right? That's what we just solved. So notice after that, after 100 miles, Keep On Trucking is going to be cheaper, right? Because these values here, these values are less than these values. Remember this one, I probably should have done this in a different color. This one is Move It Your Way, and then this one is Keep On Trucking. So after 100, Keep On Trucking is less expensive. Before 100, actually it's cheaper to use Move It Your Way, right? It's the same at 100 miles, and then after 100 miles, Keep On Trucking is cheaper. Okay, hopefully that made sense. Let's do one more question. Okay, so in this question we're told, Marcos purchased a card for his prepaid cell phone. His remaining balance B can be modeled by the equation B equals 25 minus 0.1 n, where n is the number of minutes he's talked since purchasing the card. Okay, so basically we're told the model, right? We're given the model up front. So we have B, and really it's a function of n in this case, is equal to 25 minus 0.1 n. By the way, you could write it like this too, right? If you want to write it in the form mx plus b, the m really here is negative 0.1 plus 25, right? Same thing. So 25 minus 0.1 n is the same as negative 0.1 n plus 25. This is a 0 here. Okay, so how much money was on the card when he purchased it? What intercept does this represent? Well, when he purchased it, the number of minutes he's talked is 0, right? So the balance on the card when he purchased it must be the balance when the input, the n, is 0. And obviously, what is that? It's 25 minus 0.1 times 0. So that's simply equal to 25, right? It's 25 is like the initial starting value, or the y-intercept, but in this case, since b, we're using b instead of y, this intercept is really the b-intercept. Okay, so this is like the b-intercept. Right, but that's the amount that was on the card, $25 initially. Okay, what about the second question? How many minutes will he have talked when he runs out of money? What intercept does this represent? Okay, so if he runs out of money, that means his balance is 0, right? So we basically want to set b equal to 0. And then we want to solve for the number of minutes he's talked. Solve for n. So set b equal to 0 and solve for n. So in this case, I'm going to have negative 0.1 n plus 25 equals 0. So let's solve that for n. So I'll subtract 25. So I have negative 0.1 n is equal to negative 25. Then if I divide by negative 0.1, negative 0.1, n is going to be, let's see, positive, and I guess it's divided by 10, so it's going to be 250, right? So n is 250, and remember, it has units of minutes. Okay, so what it's saying is that the balance is 0. He's going to run out of money after he talks for 250 minutes, right? When n is 250 minutes, then the balance is 0. Okay, which again, it makes sense if you think about it, right? The card had $25 on it to start, and then for each minute that he talks, the slope, the rate of change, is negative $0.1 per minute, right? Or negative 10 cents. $0.1, same thing as 10 cents. So for every minute that he talks, the balance is going to be decreasing by 10 cents. So after 250 minutes, the balance will be 0. Okay. Oh, and the last question we kind of already answered, but let's do this again. So what is the slope of the equation? What are the units? Well, we said earlier that the slope must be 0.1, right? But negative. So negative 0.1. And it has minutes. It has units of dollars per minute. Okay, or you could say, sometimes you write like this, dollars over minutes. Okay, so basically that means that the balance decreases, right? That's what the negative tells us. Decreases by $0.1, which is the same thing as 10 cents per minute, right? Every minute. Let me write that cleaner here. So decreases by $0.1, which is equal to 10 cents every minute. Okay, so that's what the slope represents. And we already know that the initial value, right, was the b-intercept, which was the $25 here, right? So that's how we got that linear equation to begin with. I'll use this one. Negative 0.1 n plus 25, right? So it's mn plus b in this case, little b. Okay, so that's it for basic linear functions. The next section is going to be on systems of two linear functions, right? Systems of linear equations, and we're going to focus just on two variables. So basically, they're going to be two linear equations. And we'll talk about how to solve those systems. We'll talk about what they represent graphically, what the solution represents graphically. And then we'll do a few applications that involve systems of linear equations. Great, thanks.